Hello everyone. Today we'll study the introduction to determinant. What is a determinant? Before I introduce what is a determinant, let me first of all give you some basic idea about determinant. The determinant of a square matrix is a scalar value, which can be used to determine whether a square matrix is invertible, or it can be used to solve a system of linear equations, or it can be used to find area and volumes in R2 and R3, etc. Next, let me introduce some simple determinant. Determinant of a 1x1 matrix. Let A be a 1x1 matrix. 1x1 matrix means it only has one row and one column. Let A be a 1x1 matrix. Then determinant of this matrix A is an entry A here. If there's only one entry, determinant of this matrix is this entry itself. That's how we find determinant for a 1x1 matrix. Determinant for 2x2 matrix, which we already seen in chapter 1. Let A be a 2x2 matrix, A, B, C, D. Determinant of matrix A is AD minus BC. That's determinant of a 2x2 matrix. Those are the simplest case. Next, let's look at some simple examples here. Find a determinant for each of the following matrices. How do we find determinant for matrix A? Here, A is a 1x1 matrix. There's only one entry here. So determinant of matrix A is this entry itself. How about determinant of matrix B? Again, B is a 1x1 matrix. There's only one entry. So determinant of matrix B is this entry itself, which is -5. How about determinant of matrix C? C is a 2x2 matrix. So for determinant of 2x2 matrix, the formula is AD minus BC. So 6 times 4 is 30. 4 times 7 is 28. 30 minus 28 is 2. So determinant of matrix C is 2. How about determinant of matrix D? Again, here D is a 2x2 matrix. For determinant of 2x2 matrix, use the formula AD minus BC, which is -24 minus -5. -24 minus -5 is -19. That's determinant of matrix D. So finding determinant for 1x1 and 2x2 matrices is easy. However, finding determinant for higher dimensional matrices is not easy. I'll show you next. Next, before I show you how to find determinants for higher dimensional matrices, let me first of all show you a notation. Let A be a square matrix. The notation A sub I comma j denotes a submatrix of A, obtained by removing the ith row and the jth column from matrix A. So A sub I comma j, I stands for ith row, j stands for jth column. So this matrix is obtained from matrix A by removing the ith row and the jth column. For example, let A be a 4x4 matrix, and let B be a 3x3 matrix. Find the submatrix A sub 1, 3. How do we find A sub 1, 3? A sub 1, 3 is a submatrix obtained from matrix A by removing the first row and the third column. If I remove the first row and the third column, what's left is this. What's left is this. That's a 3x3 matrix. If I remove the first row and the third column, that's what's left here. So what's left is A21, A22, A24, A31, A32, and A34. Then A41, A42, A44. If I remove the first row and the third column, that's what's left. A21, A22, A24 in the first row, A31, A32, A34 in the second row, A41, A42, A44 in the third row. That's the submatrix A sub 1 comma 3. How about the submatrix A sub 2 comma 1? The submatrix A sub 2 comma 1 means I remove the second row and the first column from matrix A. Remove the second row and the first column from matrix A. If I remove the second row and the first column from matrix A, if I remove the second row and the first column, that's what's left. What's left is A12, A13, A14 in the first row, A32, A33, A34 in the second row, A42, A43, A44 in the third row. If I remove the second row and the first column, that's what's left. A12, A13, A14 in the first row, and then the rest in the second row and the third row. If I remove the second row and the first column from matrix A. Now, how about the submatrix A32? The submatrix A32, I remove the third row and the second column. For the submatrix A32, I remove the third row and the second column from matrix A. If I remove the third row and the second column, that's what's left. If I remove the third row and the second column, that's what's left here. So that's A11, A13, A14, A21, A23, A24, A41, A43, and A44. That's a submatrix by removing the third row and the second column. That's a submatrix obtained by removing the third row and second column. That's what we get. That's a submatrix A sub 3 comma 2. Next, how about the submatrix B sub 1 comma 3? B sub 1 comma 3. I remove the first row and the third column from matrix B. If I remove the first row and the third column from matrix B, what's left is this submatrix here. 3, 5, 6, 8. If I remove the first row and the third column, that's what's left here. 3, 5, 6, 8. How about B sub 2 comma 1? B sub 2 comma 1. I remove the second row and the first column. B sub 2 comma 1. Remove the second row and the first column from matrix B. That's a submatrix by removing the second row and the first column from matrix B. Second row and the first column. What's left is 7, 1, 8, 9. If I remove the second row and the first column, what's left is 7, 1, 8, 9. That's a submatrix B sub 2 comma 1, obtained from matrix B by removing the second row and the first column. Second row, first column. That's what I get here. How about B sub 2, 2? B sub 2 comma 2. That's a submatrix obtained from matrix B by removing the second row and the second column. If I remove the second row and the second column, what's left is these four corners. 2, 1, 6, 9. If I remove the second row and the second column, what's left is these four corners. 2, 1, 6, 9. That's a submatrix B sub 2 comma 2. Next, let me introduce minor and cofactor. Let A be a square matrix. The Aij represent entries in the ith row and the jth column. The minor of the entries Aij, denoted by Mij, is defined as Mij equal to determinant of the submatrix A sub I comma j. The submatrix A sub I comma j is obtained from matrix A by removing the ith row and the jth column. The cofactor of Aij, denoted by Cij, is defined as Cij equal to -1 to the power of I plus j times Mij. Next, let's look at some examples. Let A be a 3 by 3 matrix. Find the value of all minors and all cofactors. Let's find the value for all minors first. How many minors do we have? Since A is a 3 by 3 matrix, there are 9 different entries, so we have 9 minors. First minor, M11. M11 is the determinant of the submatrix A sub 1, 1. The submatrix A sub 1, 1 is obtained from matrix A by removing the first row and the first column. If I remove the first row, first column, what's left is the matrix -3, 6, 4, 3. If I remove the first row, first column, that's what's left. Then take determinant, that's -9 minus 24, which is -33. That's M11. Next, find M12. M12, by definition, that's determinant of the submatrix A sub 1, 2. That's a submatrix obtained from matrix A by removing the first row in the second column. In matrix A, if I remove the first row in the second column, what's left is this entry here. 5, 6, -2, -2, and 3. I remove the first row and the second column, that's what's left. Then find determinant, I get 15 minus -12. 15 minus -12 is 27. Next, find M13. That's determinant of the submatrix A sub 1, 3, which is obtained from matrix A by removing the first row and the third column. Remove the first row and the third column, what's left is this matrix here. 5, -3, -2, and 4. And then take determinant. That's 20 minus 6, I get 14. That's the minor M13. Next, let's find M21, the minor M21. That's the determinant of the submatrix A sub 2, 1, which is obtained from matrix A by removing the second row and the first column. If I remove the second row and the first column, what's left is 1, -4, and 4, 3. Remove second row, first column, that's what's left. 1, -4, 4, 3. Then take determinant. I get 3 minus -16, which is 19. Next, let's find M22. M22, by definition, is a determinant of the submatrix A sub 2, 2, which is obtained from matrix A by removing the second row and the second column. If I remove the second row and second column, what's left is these 4 corners. 2, -4, -2, and 3. Then find determinant. It's 6 minus 8. 6 minus 8 is -2. That's M22. Next, let's find M23. M23, by definition, is the determinant of the submatrix A sub 2, 3, which is obtained from matrix A by removing the second row in the third column. Let me copy matrix A here first. Matrix A is the matrix 2, 1, -4. 5, -3, 6. -2, 4, 3. That's matrix A. For A sub 2, 3, I remove the second row and the third column. What's left is the matrix 2, 1, -2, 4. Then take determinant. I get A minus -2. A minus -2 is 10. Next, let's find M31. M31, by definition, is a determinant of the submatrix A sub 3, 1, which is obtained from matrix A by removing the third row in the first column. If I remove the third row in the first column, that's what's left. That's the matrix 1, -4, -3, and 6. Take determinant, we get 6 minus 12. 6 minus 12 is -6. Next, let's find M32. For M32, by definition, that's the determinant of the submatrix A sub 3, 2, which is obtained from matrix A by removing the third row in the second column. If I remove the third row in the second column, that's what's left here. 2, 4, 5, 6. 2, -4, 5, 6. If I remove the third row in the second column, I get 2, -4, 5, 6. Then take determinant. That's 12 minus -20. 12 minus -20 is positive 32. Next, find M33. By definition, M33 is the determinant of the submatrix A sub 3, 3, which is obtained from matrix A by removing the third row in the third column. If I remove the third row in the third column, that's the matrix 2, 1, 5, -3. Take determinant, that's -6 minus 5, which is -11. So those are the minors. Those are the value of all minors. Next, let's find a value for all cofactors. Let's find a value for all cofactors. C11. Here I is 1, J is 1. By definition, it's -1 to the power of I plus J, which is 1 plus 1, times M11. -1 to the power 2 is +1. M11 is -33. 1 times -33 is -33. C12, here I is 1, J is 2. That's -1 to the power of 1 plus 2 times M12. -1 raised to power 3 is -1. M12 is 27. -1 times 27 is -27. That's C12. Next, find C13. C13 is -1 to the power of 1 plus 3 times M of 13. -1 to the power of 4 is +1. M13 is 14. M13 is 14. 1 times 14 is 14. Next, let's find C21. C21 by definition is -1 to the power of 2 plus 1 times M21. -1 raised to power 3 is -1. M21 is 19. -1 times 19 is -19. Next, find C22. C22 is -1 to the power of 2 plus 2 times M22. -1 to the power of 4 is +1. M22 is -2. 1 times negative 2 is negative 2. That's C22. Next, find C23. C23 by definition is negative 1 to the power of 2 plus 3 times M23. Negative 1 to the power of 5 is negative 1. M23 is 10. Negative 1 times 10 is negative 10. Next, for C31, we have negative 1 to the power of 3 plus 1 times M31. Negative 1 to the power of 4 is positive 1. M31 is negative 6. 1 times negative 6 is negative 6. Next, let's find C32. C32 is negative 1 to the power of 3 plus 2 times M32. Negative 1 to the power of 5 is negative 1. M32 is 32. Negative 1 times 32 is negative 32. Next, C33 is negative 1 to the power of 3 plus 3 times M33. Negative 1 to the power of 6 is positive 1. M33 is negative 11. If we multiply, we get negative 11. So those are the values of all cofactors. Next, let's observe the values of the cofactor and the minors. We can see that they are almost the same. The only difference is that for each cofactor, we multiply the corresponding minors by negative 1 to the power of I plus j. And we know that negative 1 raised to any power, answer is either positive 1 or negative 1. When exponent is even, we get positive 1. When exponent is odd, we get negative 1. So think of this, it may be a little easier. Think of this way. In a matrix, for the first entry, I is 1, j is 1, negative 1 to the power of 1 plus 1 is positive 1. For the next entry, j stays the same, but I increased by 1, so the power will be odd. Negative 1 raised to odd power is negative. Next entry, we increased I by another 1. Odd number plus 1 will be even. So we get negative 1 raised to even power, which is positive. So we can see the sign alternating, positive, negative, and so on. In the second row, I stays the same, but j increased by 1. If j increased by 1, I stays the same. The power will be odd. Negative 1 raised to odd power is negative. Next entry, we increase I by 1. Odd number plus 1 will be even. Next, increase I by 1. Even number plus 1 will be odd. Negative 1 raised to odd power is negative. And we can see that the sign alternating. As I increase, the sign is alternating. And so on. That works for matrix in any size. So keeping this idea in mind, we can find a cofactor in a much quicker way. For example, C11, that's in the first row, first column is positive. So that's positive M11, equal to positive M11. M11 is negative 33. So positive negative 33 is negative 33. Positive negative 33 is negative 33. It stays the same. For C12, that's negative. That's negative M12. Negative M12 means we change the sign. Negative M12 means we switch the sign. So for negative M12, we switch the sign. Positive 27 becomes negative 27. For C13, entry is here. The sign is positive. So keep positive sign. That's positive of M13. Positive M13 means M13 stays the same. M13 stays the same. M13 is 14, so we leave it the same. Then next row, for C21, second row, first column is here. The sign is negative. So take negative M21. M21 is 19. This negative M21 means I switch the sign. So positive 19 becomes negative 19. For C22, entry is here, which is positive. The sign is positive. Take positive sign. Positive M22. Positive M22 means M22 stays the same. Here M22 is negative 2. So it stays the same. Next, for C23, the sign here is negative. That's negative M23. M23 is 10. Negative M23 means I switch the sign. Positive 10 becomes negative 10. Next, for C31, it's here. Third row, first column. The sign is positive. It's positive M31. Positive M31 means everything stays the same. That's exactly the same as M31. M31 is negative 6. So C31 is negative 6. For C32, third row, second column, the sign is negative here. That's negative M32. M32 is 32. Negative M32 means I switch the sign. This number is positive, we make it negative. Next, for C33, the sign here is positive. That's positive M33. Positive M33 means it stays the same. It's exactly the same as M33. M33 here is negative 11. So C33 is also negative 11. Doing this way, it's quicker than computing negative 1 to the power of I plus j. So doing this way, memorize the table. Doing this way, it's easier than computing negative 1 to the power of I plus j. So that's a quicker way to get cofactors from minors. Next, let me introduce cofactor expansion. Let A be an n by n square matrix. That's matrix A. That's the first row, second row, the nth row. That's the first column, second column, the nth column. The expression A11 times C11 plus A12 times C12 plus plus A1n times C1n. Let's call the cofactor expansion along the first row. A11 plus C11 plus A12 times C12 plus A1n times C1n. Let's call the cofactor expansion along the first row. Similarly, the expression A21 times C21 plus A22 times C22 plus A2n times C2n. Let's call the cofactor expansion along the second row, and so on. Similarly, to define the third row, fourth row, and nth row. The expression A11 C11 plus A21 C21 plus AN1 CN1. This is called the cofactor expansion along the first column. The expression A12 plus C12 plus A22 times C22 plus plus AN2 times CN2. That's called the cofactor expansion along the second row, along the second column. That's how we define cofactor expansions. Next, let's create an example. In the previous example, find the cofactor expansion along each row and each column. In the previous example, A is a 3 by 3 matrix. We try to find the cofactor expansion along each row and each column. Let's first of all find the cofactor expansion along the first row. A is a 3 by 3 matrix. Cofactor expansion along the first row is A11 times C11 plus A12 times C12 plus A13 times C13. Then plug in numbers. A11 is 2. C11 is negative 33. A12 is 1. C12 is negative 27. A13 is negative 4. C13 is 14. Then multiply. 2 times negative 33 is negative 66. 1 times negative 27 is negative 27. 4 times 14 is negative 56. Adding up, I get negative 149. That's the covert expansion around the first row. Next, find the covert expansion around the second row. That's the second row here. So the covert expansion is A21 times C21 plus A22 times C22 plus A23 times C23. Then plug in numbers. A21 is 5. C21 is negative 19. A22 is negative 3. C23 is negative 2. A23 is 6. C23 is negative 10. Then multiply. 5 times negative 19 is negative 95. Negative 3 times negative 2 is positive 6. 6 times negative 10 is negative 60. Adding up, we get negative 149. Next, find the covert expansion around the third row. That's the third row here. The covert expansion around the third row is A31 times C31 plus A32 times C32 plus A33 times C33. Then plug in numbers. A31 is negative 2. C31 is negative 6. A32 is positive 4. C32 is negative 32. A33 is positive 3. C33 is negative 11. Then calculate. Negative 2 times negative 6 is positive 12. 4 times 32, negative 32 is negative 128. 3 times negative 11 is negative 33. Then, adding up, I get negative 149. That's the covert expansion around the third row. Next, find the covert expansion around the first column. Around the first column, we have A11 times C11 plus A21 times C21 plus A31 times C31. Then plug in numbers. A11 is 2. C11 is negative 33. A21 is 5. C21 is negative 19. A31 is negative 2. C31 is negative 6. Then adding up. 2 times negative 33 is negative 66. 5 times negative 19 is negative 95. 2 times negative 6 is positive 12. Adding up, I get negative 149. Next, find the covert expansion around the second column. That's the second column here. We have A12 times C12 plus A22 times C22 plus A32 times C32. Then plug in the values. A12 is 1. C12 is negative 27. A22 is negative 3. C22 is negative 2. A32 is 4. C32 is negative 32. multiply and add them up. I get negative 27 plus 6 minus 128, which is negative 149. That's the covalent expansion around the second column. Next, find the covalent expansion around the third column. That's the third column here. Around the third column, we have A13 times C13 plus A23 times C23 plus A33 times C33. Then plotting numbers and add them up. A13 is negative 4. C13 is 14. A23 is 6. C23 is negative 10. A33 is 3. C33 is negative 11. Then multiply and add them up. We get negative 56 minus 60 minus 33. Add them up, I get negative 149. That's the covalent expansion around the third column. So here you can see that covalent expansion around each row and each column all turn out the same value. Covalent expansion around all rows and all columns turn out exactly the same values. So based on the previous example, we have the following theorem. For any n by n square matrix A, its covalent expansion along each row and each column is always the same. For any n by n square matrix A, its covalent expansion along each row and each column is always the same. They are all the same. That's what this theorem says. Next, let me give a formal definition for determinant. If A is a 1 by 1 matrix, 1 by 1 matrix means A has only one row and one column. There's only one entry. Then determinant of A equal to this entry. If A is a 1 by 1 matrix, then determinant of A equal to this entry. If A is a n by n square matrix with n greater or equal to 2, if A is an n by n square matrix with n greater or equal to 2, then its determinant is defined as covalent expansion along any row or any column. Since they are all the same, determinant of A is defined as the covalent expansion along any row or any column, since they are all the same. Next, let me show you some notation for determinant. Determinant of A, sometimes we can write it as 2 bars and put A in the middle. For example, for determinant of this 2 by 2 matrix, I can write it as 2 bars with a matrix in the middle. Next, let's create a theorem. Let A be a 2 by 2 matrix A, B, C, D. Then determinant of A is AD minus BC. We use this formula very, very frequently, but we never give a proof. Let's prove it. Try to prove determinant of A equal to AD minus BC. How can we prove it? Using the definition, determinant of A could be the covalent expansion along any row or any column. So let me find determinant of A by finding covalent expansion around the first row. So let determinant of A equal to the covalent expansion along the first row. That equal to A times C11 plus B times C12. A times C11 plus B times C12. And we know that the signs alternating for covert, the signs alternating positive, negative, negative, positive. The signs alternating. So I can write it as positive A times M11 minus B times M12. What's M11? What's M12? M11 is the determinant of the matrix, of the submatrix A sub 1, 1. M12 is the determinant of the submatrix A sub 1, 2. The submatrix A sub 1, 1 is a matrix obtained from matrix A by removing the first row and the first column. This is submatrix obtained from matrix A by removing the first row and the first column. If I remove the first row and the first column, what's left is D. Its answer is D. What's left is a 1 by 1 matrix D. And submatrix A sub 1, 2 is a matrix obtained from matrix A by removing the first row and the second column. If I remove the first row and the second column, what's left is entry C. That's a 1 by 1 matrix C. And we know that for 1 by 1 matrix, the determinant is the entry itself. For 1 by 1 matrix, the determinant is the entry itself. And for 1 by 1 matrix, the determinant is the entry itself. That's why determinant of A is AD minus BC. That's the proof. Next, let's look at some examples. Find a determinant for each of the following matrices. Here we have A, B, C, D, 4 matrices. Find determinant for each of them. Let's find determinant for matrix A first. For determinant of A, we can find a covert expansion around any row or any column, since they are all the same. In general, we find a covert expansion around the first row. So let's find a covert expansion around the first row. I have 3 times C11 plus 2 times C12 plus 4 times C13. And we know that the sign alternating. The sign of covectors is alternating. Plus, minus, and so on. Minus, plus, and so on. Plus, minus. The sign alternating. So, first entry C11 is positive. It's 3 times M11. Second entry is negative. It's 2 times M12. It's negative. Next entry is positive. So we have positive 4 times M13. M11 is the minor, which is the determinant of the submatrix A sub 1, 1. M12, that's the determinant of the submatrix A sub 1, 2. M13, that's the determinant of the submatrix A sub 1, 3. Determinant of A sub 1, 1. That's a matrix obtained from matrix A by removing the first row and first column. If I remove the first row, first column, what's left is the matrix 6, -5, 1, -2. The submatrix A sub 1, 2. That's a matrix obtained from matrix A by removing the first row and the second column. If I remove the first row and second column, what's left is -1, -5, -3, and -2. And 4 times determinant of A sub 1, 3. That's a submatrix obtained from matrix A by removing the first row and the third column. If I remove the first row and the third column, that's what's left. -1, 6, -3, 1. If we simplify, we have 3 times -12 minus -5. -2 times 2 minus 15 plus 4 times -1 minus -18. Together we have 3 times -7 minus 2 times -13 plus 4 times 17. 3 times -7 is -21. -2 times -13 is +26. 4 times 17 is 68. -21 plus 26 is +5. 5 plus 68 is 73. That's determinant of matrix A. Next, let's find determinant of matrix B. For determinant of matrix B, we can find a covalent expansion around any row or any column, since they're all the same. In general, we find a covalent expansion around the first row. So find a covalent expansion around the first row. And we know that the sign of the cofactors alternating. So I can write it as positive 4 times M11 minus 1 times M12 plus negative 5 times M13. That's the covalent expansion around the first row. Then we know that M11 is the determinant of the submatrix by removing first row, first column from matrix B. Removing first row, first column from matrix B. What's left is negative 2, 0, 9, 2. Negative 1 times M12. M12 is the determinant of a submatrix by removing first row and second column from matrix B. Remove first row, second column. What's left is 3, 0, 7, 2. Remove first row, second column. What's left is 3, 0, 7, 2. 1 times determinant of the matrix, 3, 0, 7, 2. Positive negative is negative. 5 times M13. M13 is the determinant of the submatrix by removing first row and third column from matrix B. If I remove the first row and third column, that's what's left. So 5 times determinant of the matrix, 3, negative 2, 7, 9. These two bars represent determinant. Then simplify. Take determinant here, negative 4 minus 0. 6 minus 0. 27 plus 14. Negative 4 minus 0 is negative 4. 6 minus 0 is 6. 27 plus 14 is 41. Multiply, I get negative 16 minus 6 minus 205. Together is negative 227. That's the determinant of matrix B. Now, for matrix B, is there a better way? Is there an easier way to find determinant? Is there an easier way to find determinant? Remember, we can find covalent expansion around any row or any columns. Or if I find the determinant, or if I find a covalent expansion around the second row, what do we get? If I find a covalent expansion around the second row, will it be easier? Let's try. If I find covalent expansion around the second row, what do I get? Is it easier or not? Around the second row, I have here the signs alternating. Negative, positive, negative, positive. So I get negative 3 times M21 plus negative 2, the sign alternating, plus negative 2 times M22 minus 0 times M23. We know that 0 times M23 is 0. So what's left is negative 3 times M21. For M21, that's a determinant of the submatrix by removing second row and the first column from matrix B. If I remove the second row and the first column, what's left is 1, negative 5, and 9, 2. Plus minus means minus 2 times M22. M22 is the determinant of the matrix. It's the determinant of the submatrix by removing the second row and second column from matrix B. If I remove second row, second column, what's left is these four corners. So we have 4, negative 5, 7, 2, minus 0. Here we only need to compute 2 determinants. That's easier than doing this way. We need to compute all 3 determinants. 1 times 2 is 2. 9 times negative 5 is negative 45. 2 minus negative 45 is 2 plus 45. 4 times 2 is 8. 7 times 5. 7 times negative 5 is negative 35. So we get 8 plus 35. Together we have negative 3 times 47 minus 2 times 43. Negative 3 times 47 is negative 141. 2 times 43 is 86. It's negative 86. Together we have 227, negative 227. We get exactly the same answer. But doing this way, we only compute two determinants. That's a little easier than solving in this way. So in general, think of when we find Covert expansion in a row or column, the more zero, the easier it is. When we try to find determinant in a row or columns, the more zero, the easier it is. Next, let's find determinant of matrix C. We know that for determinant of matrix C, we can find a covert expansion around any row or any column. Any row, any column. Here we can see that in the third column, there are two zeros. If I find a covert expansion around the third column, it will be much, much easier. Let's find a covert expansion around the third column. In the third column here, the sign alternating. Positive, negative, positive, negative. So, first term is positive. 2 times M13 minus 0 times M23 plus 0 times M33 minus negative 4 times M43. So those two terms become 0. What's M13? M13 is a determinant of the submatrix by removing the first row and the third column from matrix C. The submatrix by removing the first row and the third column from matrix C. What's left is this submatrix. 5, negative 6, 7, 3, negative 1, 6, 2, 9, 8. This term becomes 0, this term becomes 0. Here, negative, negative 4, double negative is positive. 4 times M43. M43 is a submatrix by removing determinant of the submatrix by removing the fourth row and the third column. So, removing the fourth row and the third column, that's a submatrix. I get 4, 1, 3 in the first row, 5, negative 6, 7 in the second row, 3, negative 1, 6 in the third row. Then compute this 3 by 3 matrix. For 3 by 3 matrix, we can compute the covert expansion around any row or any column. Since there are no zeros, it doesn't matter which row we choose, they are the same. So let me find a covert expansion around the first row. Let me find a covert expansion around the first row. The sign is alternating, plus minus plus in the first row. So I get 5 times M11. I cross our first row, first column. What's left is negative 1, 6, 9, 8. Next is minus negative 6 times M12, which means I cross out first row, second column. Negative 6 is here. Cross out first row, second column. What's left is 3, 6, 2, 8 plus 7 times M13. 7 is here. Cross out first row, third column. It's a determinant of the matrix 3, negative 1, 2, 9. Plus 4 times determinant of this 3 by 3 matrix. Since there are no zeros, we can pick any row, any column. In general, let me choose the first row. 4 times the determinant of the submatrix. Negative 6, 7, negative 1, 6. Minus 1. Cross out first row, second column. 1 times determinant of the submatrix. 5, 7, 3, 6 plus 3 times the determinant of the submatrix by crossing out first row, third column. I have a submatrix 5, negative 6, 3, negative 1. That's 2 times 5 times here. Negative 1 times a is negative a. 9 times 6 is 54. Negative a minus 54 is negative 62. Double negative is positive. 3 times a is 24. 2 times 6 is 12. 24 take away 12 is 12. Plus 7 times 3 times 9 is 27. 2 times negative 1 is negative 2. 27 minus negative 2 is 29. Plus 4 times negative 6 times 6 is negative 36. Negative 1 times 7 is negative 7. Negative 36 minus negative 7 is negative 29. Minus 1 times 5 times 6 is 30. 3 times 7 is 21. 30 minus 21 is 9. Plus 3 times the determinant of the third matrix. For the third matrix, I make a mistake here. It should be 5, negative 6, 3, negative 1. 5 times negative 1 is negative 5. 3 times negative 6 is negative 18. Negative 5 minus negative 18 is positive 13. Then continue. 5 times negative 62 is negative 310. 6 times 12 is 72. 7 times 29 is 203. 4 times negative 29 is negative 116. Negative 1 times 9 is negative 9. 3 times 13 is 39. Then negative 310 plus 72 plus 203 is negative 35. And negative 116 minus 9 is negative 125. Negative 125 plus 39 is negative 84. Negative 86. 2 times negative 34 is negative 70. 4 times negative 86 is negative 344. Together is negative 414. That's the determinant of matrix C. That's the determinant of matrix C. Next, find determinant of matrix D. For matrix D, we can find determinant, we can find a covalent expansion along any row or any column. Here we can see that in the first column, we have 4 zeros. If I find determinant over the first column, it will be much easier. So let's find a covalent expansion around the first column. It will be 6 times M11. Here the sign is positive, negative, and so on. The sign is alternating. Next is 0 times M12, M21, plus 0 times M31, minus 0 times M41, plus 0 times M51. Those are all zeros. What's left is 0 times M11. M11 is the determinant of the matrix, determinant of the submatrix by crossing out first row, first column. Since it's here, cross out first row, first column, that's the submatrix. So what we have here is 4, negative 3, A, negative 9, 0, negative 1, negative 10, and 4, 0, 0, 2, negative 7, 0, 0, 0, negative 5. The rest are zeros. Now, find determinant for this 4 by 4 matrix. We can find determinant we can find a covert expansion around any row or any column. We can find a covert expansion around any row or any column. The more zero, the easier it is. If I find a covert expansion around the first column, we can see that there are 3 zeros. So I have 4 times M11. The sign is alternating, plus minus plus minus. Minus 0 times M21 plus 0 times M31 minus 0 times M41. Those are all zeros. What's left is 6 times 4 times M11. For M11, number 4 is here, cross out first row, first column, that's a submatrix. So for determinant for the submatrix, -1, -10, 4, 0, 2, -7, 0, 0, -5. Then for determinant for this 3 by 3 matrix, we can find covert expansion around any row, any column. The more zero, the easier it is. Here, if I find covert expansion around the first column, we have 2 zeros. So use covert expansion around the first column. We have M1, -1 times M11. The sign is alternating, positive, negative. 0 times M21 plus 0 times M31. Those are zeros. What's left is 6 times 4 times -1 times M11. M11 is a determinant of the submatrix by crossing out first row and first column. That's a submatrix. For determinant for 2, -7, 0, -5. Then we can provide covert expansion again. We can find covert expansion around any row, any column. The more zero, the easier it is. Let me find covert expansion around the second row, around the first column. I get 6 times 4 times -1 times 2 times M11 minus 0 times M21. Find covert expansion around the first column here. The sign is alternating, positive, negative, and so on. And 0 times M21 is 0. What's left is 2 times M11. They equal to 6 times 4 times -1 times 2 times M11. M11 is a determinant of the submatrix by removing the first row and the first column. What's left is a 1 by 1 matrix 5. This represents determinant, doesn't mean absolute value. This represents determinant. It doesn't mean absolute value. This represents determinant of -5. It doesn't mean absolute value. Determinant of -5 is also -5. So you get 6 times 4 times -1 times 2 times -5. So you can see that if I multiply up, that's a determinant. 6 times 4 is 24. -1 times -4 is positive 5. 5 times 2 is 10. 24 times 10 is 240. That's a determinant of matrix D. That's a determinant of matrix D. Here, if we observe matrix D, we can see that D is the upper triangular matrix, and its determinant is the product of all entries in the main diagonal. Based on the previous example, we have the following theorem. Let A be an m by m matrix. If A is an upper triangular, lower triangular, or diagonal matrix, then determinant of A can be computed by multiplying all entries in the main diagonal. If a matrix is upper triangular matrix, then its determinant can be computed by multiplying all entries in the main diagonal. The same rule works for lower triangular and diagonal matrix. Let's prove it here. Let A be an upper triangular matrix. A11, A12, A1n. 0, A22, A2n, ANN. The rest are zeros. That's an upper triangular matrix. For determinant of matrix A, if I take covalent expansion around the first column, I get A11 times determinant of the submatrix by crossing out first row, first column. That's A22, A23, A2n, 0, A33, A3n, ANN. The rest are zeros. Again, this is also upper triangular matrix. I can again take determinant, take a covalent expansion around the first column. I get A11 times A22. Take a covalent expansion around the first column. I get A22 times the submatrix here. A33, A34, A3n, 0, A44, A4n, ANN in the last row, 0, 0. If we continue the process by keep taking covalent expansion along the first column, eventually we'll get A11 times A22 times A33 times ANN. That's the product of all entries in the main diagonal. So determinant of A is a product of all entries in the main diagonal if A is upper triangular matrix. The proof is very similar when A is a lower triangular matrix or when A is diagonal matrix. Next theorem. Let A be an m by n square matrix. Then determinant of A transpose equal to determinant of A. How can we prove this theorem? In order to prove this theorem, we need to use mathematical induction. Next, let me introduce mathematical induction. In order to prove a statement is true for n equal to 1, 2, 3, 4, 5, and so on, we can use mathematical induction. For this theorem, we try to prove that determinant of A transpose equal to determinant of A for any m by n square matrix. For any m by n square matrix means the matrix could be 1 by 1, 2 by 2, 3 by 3, and so on, which means n could be 1, 2, 3, 4, 5, and so on. So for this theorem, we try to prove that determinant of A transpose equal to determinant of A for n equal to 1, 2, 3, 4, 5, and so on. So for this theorem, we can use mathematical induction to prove it. So in order to prove a statement is true for n equal to 1, 2, 3, 4, 5, and so on, we can use mathematical induction. The proof contains two steps. The basic step and the inductive step. The basic step says that prove that the statement is true for n equal to 1. And for the inductive step, assume the statement is true for n equal to k minus 1. We need to prove that the statement is also true for n equal to k. If both of them are true, then the statement is true for n equal to 1, 2, 3, 4, 5, and so on. That's called proof by mathematical induction. How does that make sense to you? Think of this. Let's think of the list of domino cards. Assume that's the first card n equal to 1, second card n equal to 2, third card n equal to 3, n equal to 4, 5, and n equal to k minus 1, n equal to k. Think of a list of domino cards. If the statement is true for n equal to 1, that means we can hit the first card. If the statement is true when n equal to k minus 1, then the statement is also true when n equal to k. That means every card can hit the next card. That means the card k minus 1 can hit the card of k. That means every card can hit the next card. If I can hit the first card, and every card can hit the next card, then the entire list will be hit. That's why the statement is true. If both of them are true, the statement is true for every n equal to 1, 2, 3, 4, 5, and so on. That's called proof by mathematical induction. Now go back to this theorem here. If we try to prove by mathematical induction, proved by mathematical induction on n. Here n could be 1, 2, 3, 4, 5, and so on. The size must be at least 1 by 1. It cannot be 0 by 0. So for basic step, try to show that the statement is true when n equal to 1. When n equal to 1, A is a 1 by 1 matrix. If n is 1 by 1, then A has only one entry. If A is 1 by 1, A has only one entry, which is, let's call this entry A. And A transpose will also be A. Hence, determinant of A transpose equal to A, which is also the same as determinant of A. So the statement is true when A equal to 1. Here I prove that determinant of A transpose equal to determinant of A when A equal to 1. That's called basic step. Next, the inductive step. Assume the statement is true when A equal to K minus 1. So what do we assume here? Assume determinant of A transpose equal to determinant of A for any K minus 1 by K minus 1 matrix. Assume determinant of A transpose equal to determinant of A for any K minus 1 by K minus 1 matrix A. Assume this statement is true for any K minus 1 by K minus 1 matrix A. Here I plug in K minus 1 for each n. Assume the statement is true for n equal to K minus 1. We try to prove that the statement is also true when n equal to K. We want to prove that determinant of A transpose equal to determinant of A for any m by m matrix, K by K matrix A. So here is an assumption that the statement is true when n equal to K minus 1. That's our assumption. This is called induction hypothesis. This statement is called induction hypothesis. Assume the statement is true when n equal to K minus 1. We try to prove that the statement is true when n equal to K. That's our goal. Try to prove this. So here I'll first of all set up matrix A and A transpose. Then try to show that their determinants are exactly the same using the induction hypothesis. First of all, let A be a K by K square matrix. Let A be the matrix with K rows and K columns. Let A be the matrix A11, A12, A13, A1K. Second row A21, A22, A23, and A2K. Third row A31, A32, A33, A3K. Last row will be AK1, AK2, AK3, and AKK. That's matrix A. Then, if that's matrix A, then A transpose. For A transpose, we put rows in columns. So A transpose will be the matrix A11, 2 rows in columns, A11, A12, A13, A1K in the last row. Then we have A21, A22, A23, and A2K. Next column will be A31, A32, A33, and A3K. Continue, last column. Last column will be AK1, AK2, AK3, and AKK. That's A transpose. Next, I'll compute determinant of A and determinant of A transpose and try to show that they're exactly the same. Next, let me write down determinant of A. For determinant of A, we can apply Covalent expansion on any rows or any columns. They are all the same. Here, let me find Covalent expansion along the first row. Let me find Covalent expansion along the first row. The sign of the cofactors is alternating. Plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus, and so on. That's the sign of the cofactors. So, for A11, the sign of its cofactor is positive. So I write positive A11 times determinant of the submatrix by crossing out the first row and the first column. If I cross out first row, first column, what's left is A22, A23, A2K. Second row is A32, A33, and A3K. Last row will be AK2, AK3, and AKK. That's the submatrix by crossing out the first row and first column. Next, the cofactor is negative. I write A12 times determinant of the matrix of the submatrix by crossing out the first row, second column. Here the submatrix is A21, A23 since I cross out second column, A23, A2K. Next row will be A31, A33, and A3K. In the last row, it will be AK1, AK3, and AKK. Continue, we have plus, minus, until the last entry in the first row, A1K. Since we don't know if K is even or odd, we can tell it's positive or negative. So write the sign as -1 to the power of 1 plus K. Write the sign as -1 to the power of 1 plus K times A1K times determinant of the submatrix by crossing out the first row and the case column. If I cross out the first row and the case column, that's the submatrix. So the submatrix here will be A21, A22, A2K minus 1. Since I crossed out last column, A2K, the previous entry should be A2K minus 1. The previous entry is A2K minus 1. Next row will be A31, A32 until we cross our last column will be A3K minus 1. A31, A32, last entry will be A3K minus 1. And in the last row, since I cross out last column, it will be AK1, AK2, AK3 until AK, comma, K minus 1. AK1, AK2 until AK, K minus 1. That's the determinant of the submatrix. This is determinant of A. Next, let's write down determinant of A transpose and show that they are exactly the same. For determinant of A transpose, I can take Covert expansion around any row or any column. In order to match what we have here, I'll take Covert expansion around the first column. So take Covert expansion around the first column, and the sign of the covert will be alternating, positive, negative, and so on. So first entry is A11, which is positive, time determinant of the submatrix by crossing out the first row and the first column, times this submatrix here, which is determinant of A22, A32, and AK2. Next row will be A23, A33, and AK3. The last row will be A2K, A3K, and AKK. Next, it will be negative A12 times determinant of the submatrix by crossing out the second row and the first column. If I cross out second row and the first column, the submatrix is A21, A31, and AK1 in the first row. I cross out second row, so next row will be A23, A33, and AK3. Last row will be A2K, A3K, and AKK. Then continue plus, minus. On the last entry here, we don't know if it's positive or negative because we don't know if k is even or odd. So write it as -1 to the power of 1 plus k times the entry A1k times the determinant of the submatrix. If I cross out the last row and first column, this is a submatrix. This is a submatrix. So the first row is A21, A31, and AK1. Second row will be A22, A32, and AK2. Then in the last row, since I cross out last row here, the second last row will be A2k minus 1, A3k minus 1, and AKk minus 1. That's the submatrix. Now, this is a k minus 1 by k minus 1 matrix. Because originally, A transpose is a k by k matrix. If I remove one row, one column, this is a k minus 1 by k minus 1 matrix. Same thing, this is also a k minus 1 by k minus 1 matrix. This is also a k minus 1 by k minus 1 matrix. By induction hypothesis, we know that determinant of A transpose equal to determinant of A for any k minus 1 by k minus 1 matrix A. So since this is a k minus 1 by k minus 1 matrix, this determinant equal to its transpose. This determinant equal to its transpose by induction hypothesis. By induction hypothesis, this determinant equal to its transpose. So now equal to A11 times determinant of this transpose. For the transpose per rows in columns, I get A22, A32, AK2. put rows in columns, then put second row in second column. A23, A33, AK3. Then put the last row in the last column. Okay, A2K, A3K, and AKK. Minus A12 times determinant of this transpose. By induction hypothesis, determinant of this K minus 1 by K minus 1 matrix equal to its transpose. So put rows in columns. We have A21, A31, and AK1. Put second row in the second column. We have A23, A33, AK3. Then put the last row in the last column. We have A2K, A3K, and AKK. Plus minus plus -1 to the power of 1 plus K times A1K times determinant of the transpose of this matrix. Since this is a K minus 1 by K minus 1 matrix. So put rows in columns. We have A21, A31, and AK1 in the first row, in the first column. Then put second row in the second column. We get A22, A32, and AK2. Put last row in the last column will be A2, comma K minus 1, A3, comma K minus 1, AK, comma K minus 1. If we compare this with determinant of A, we can see that this matrix is exactly the same as this matrix. This matrix is exactly the same as this matrix. And this matrix is exactly the same as this matrix. So this entire row equal to determinant of A. So they equal to determinant of A. Therefore, determinant of A transpose equal to determinant of A. For any K by K square matrix. Let's complete the proof by mathematical induction. We assume the statement is true for n equal to K minus 1, and we prove that the statement is also true for n equal to K. Let's complete the proof by mathematical induction. Next theorem, let A be a n by n matrix, and let K be a scalar. When K is multiplied to a row in A, the determinant of the new matrix is K times determinant of A. So what this theorem says is that, suppose A is a square matrix. Assume this A is a 3 by 3 matrix. For example, 1, 2, 3, 2, 1, 4, 5, 1, 1, for example. Let K be a scalar. Say K is 3. If I multiply K to one of the rows in matrix A, for example, the second row, if I multiply the second row by 3, the new matrix will be 1, 2, 3. If I multiply second row by 3, I get 6, 3, 12, 5, 1, 1. That's a new matrix. This theorem says the determinant of the new matrix is the same as K times determinant of matrix A. That's what this theorem says. You can verify this by yourself. They must be the same. You can verify this by yourself. The determinant for both of them and then multiply by 3. They must be the same. You can verify by yourself. But an example is not a proof. Let's prove this theorem. A is an n by n matrix. K is a scalar, and K is multiplied to a row in A. the determinant of a new matrix is K times determinant of A. So assume K is multiplied to the ith row in matrix A. Assume K is multiplied to the ith row in matrix A. So that's matrix A. That's the first row. That's the second row. That's the ith row. And the last row is the nth row. Assume that's matrix A. So the first row entry will be A11, A12, A13, and A1n. Entry in the second row will be A21, A22, A23, and A2n. Entries in the ith row will be AI1, AI2, AI3, and AIN. Entries in the last row will be AN1, AN2, AN3, and ANN. Next, if I multiply the ith row by K, if I multiply the ith row by K, let me write it like this. K times Ri. If I multiply the ith row by K, K times Ri, I get a new matrix. If I multiply the ith row by K, I get a new matrix. Everything else stays the same. A11, A12, A13, A1n in the first row. A21, A22, A23, A2n in the second row. If I multiply the ith row by K, it will be KAI1, KAI2, KAI3, and KAIN in the ith row. The rest stays the same. AN1, AN2, AN3, and ANN. That's the new matrix. Let me call this new matrix B. Let me call this new matrix B. Next, we try to find determinant of B and show that that's the same as K times determinant of A. For determinant of B, I'll take covalent expansion around the ith row. So, for covalent expansion, the sign for the covector alternating: positive, negative, positive, negative, positive, negative, and positive, negative, positive. The sign of covector alternating. In the ith row, since we don't know I is positive or negative, so let me write it as -1 to the power of I plus 1. Since we don't know I is positive or negative, so write it as -1 to the power of I plus 1 times the entries. Entry is KAI1 times determinant of the submatrix by crossing out the ith row first column. So that's a submatrix from matrix B by crossing out the ith row and the first column. Next, plus -1 to the power of I plus 2 times the second entries KAI2 times the determinant of the submatrix by crossing out the ith row and the second column. A submatrix from matrix B by crossing out the ith row and the second column. continue plus until the last entries. That's -1 to the power of I plus n times k times AIN times determinant of the submatrix by crossing out the ith row and the nth column. From matrix B, cross out the ith row and nth column. If we compare matrix A and B, we can see that the only difference is the ith row. But when we're finding the determinant here, for each submatrix, I cross out ith row. For every submatrix here, I cross out ith row. That means the submatrix BI1 is the same as the submatrix AI1. If I cross out the ith row in the first column, what's left is exactly the same as what's in matrix B. So that's the same as KAI1 times determinant of the matrix submatrix in A by removing ith row and the first column. If I remove the ith row and the first column, what's left is exactly the same in matrix B. So this and this are exactly the same. In matrix B, if I remove the ith row and the first column, what's left is the same, exactly the same as what we have in matrix A. Same thing for the next one. KAI2 times determinant of the submatrix A by removing the ith row and the second column from matrix A. The submatrix from matrix B by removing the ith row and the second column is exactly the same as the submatrix from matrix A by removing the ith row and the second column. They are exactly the same. In matrix A and B, the only difference is the ith row. If I cross out the ith row, the rest is exactly the same. Same thing for the last entry. -1 to the power of I plus n, k times AIN times determinant of the submatrix. Submatrix removing the ith row and nth column from matrix B is exactly the same as the submatrix from matrix A by removing the ith row and nth column. These are exactly the same. Next, k is a common factor. For every term, k is a common factor. If I pull out k, what do I get? If I pull out k, I get k times -1 to the power of I plus 1 times AI1 times determinant of the submatrix A sub I comma 1. That's a submatrix from matrix A by removing the ith row in the first column, plus -1 to the power of I plus 1 times AI2 times determinant of submatrix A sub I comma 2 plus -1 to the power of I plus n. I pull out k, I get AIN times determinant of the submatrix AIN. What's this? If we don't look at k here, this is the Covert expansion in matrix A along the ith row. This is the Covert expansion in matrix A along the ith row. So this is equal to the determinant of matrix A. Since this is the Covert expansion along the ith row in matrix A, this is equal to the determinant of A. So they equal to k times determinant of A. Let's complete the proof. The determinant of the new matrix is k times determinant of A. So if I multiply the ith row by a scalar k, the determinant of the new matrix is k times determinant of A. Note, for this theorem, we can memorize it in this way. Suppose we have a square matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. If I multiply one of a row by k, then when I take a determinant, they're equal to k times the determinant of an original matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. That's how we memorize this theorem. For any square matrix, if I multiply one of a row by constant k, and then the determinant of the matrix equal to k times the determinant of the original matrix. Or we can also think of, I'm factoring k out from the first row. You can also think of this way. I'm factoring k out from the first row, from one of the rows. I'm factoring k out from one of the rows. So that's how we memorize the theorem. Next theorem. Let A be a square matrix. If A has a row of zeros, then determinant of A must be 0. Let's prove it. In matrix A, assume the ith row contains all zeros. Assume the ith row contains all zeros. Then, determinant of A can be written as the determinant of, let me use bars to represent determinant. The entry in the first row is A11, A12, A1n. Entry in the second row is A21, A22, A2n. Let me call this ith first row. Assume that's the first row, that's the second row, that's the ith row, that's the nth row. First row, second row, ith row, and nth row. Assume the entry in the ith row contains all zeros. Entry in the nth row is an1, an2, ann. That's determinant of matrix A. Here in the ith row, it contains all zeros. 0 can be rewritten as 0 AI1. Second 0 can be written as 0 AI2, and so on. Last 0 can be written as 0 AIN. Let me rewrite the ith row. First 0 can be written as 0 times AI1, second 0 can be written as 0 times AI2, and the last 0 can be written as 0 times AIN. Leave the rest the same. A11, A12, A1n, A21, A22, A2n. Leave the last row the same. AN1, AN2, and ANN. Now, according to the previous theorem, if I multiply a row by a constant, I can pull out a constant. If there's a common factor, think of this as a common factor. If there's a common factor in a row, I can pull out a common factor from the row. The rest stays the same. If there's a common factor in a row, I can pull out a common factor and leave the rest the same. That's the previous theorem. So here in the ith row, we can see that 0 is a common factor. If I pull out 0, what do I get? If I pull out 0 from the ith row, all I get is 0 times the entries times the determinant of the matrix. A11, A12, A1n in the first row. A21, A22, A2n in the second row. AI1, AI2, AIN in the ith row, AN1, AN2, ANN in the nth row. And we know that 0 times everything is 0. So determinant of A equal to 0. If A has a row of 0, determinant of A equal to 0. That's the proof for this theorem. Next theorem, let A be a n by n square matrix, and let K be a scalar. Then determinant of Ka equal to K to the power of n times determinant of A. Let's prove it. Let A be an n by n square matrix. Then A can be written as A11, A12, A1n in the first row, A21, A22, A2n in the second row, AN1, AN2, ANN in the last row. Then determinant of Ka, we multiply K to every entry. For determinant of Ka, I multiply K to every entry. That's the determinant of the matrix. Ka11, Ka12, Ka1n in the first row, Ka21, Ka22, and Ka2n in the second row. Then Kan1, Kan2 and Kann in the last row. By the previous theorem here, if there's a common factor in a row, I can pull out a common factor, leave the rest the same. If there's a common factor in a row, I can pull out a common factor, leave the rest the same. So I can pull out common factor K from the first row, then pull out common factor K from the second row, and pull out common factor K from every row. There are n factors. I pull out K from each row. I pull out K from the first row, second row, third row, and nth row. So there are n factors of K. What's left is the matrix A11, A12, A1n, A21, A22, A2n, AN1, AN2, and ANN. K times K times K, if there are K factors, that's K to the power of n. If there are n factors, that's K to the power of n. And this is determinant of A. This is determinant of A. That completes the proof for this theorem. Next theorem. Let A, B, C be n by n square matrices. Assume their entries are identical everywhere, except in the ith row. If the sum of the ith row vector in matrices A and B is the same as the ith row vector in matrix C, then determinant of matrix C equal to determinant of A plus determinant of B. What does this theorem mean? Assume A, B, C are square matrices, and the entries are identical everywhere, except the ith row. For example, if A is a 3 by 3 matrix, it's 1, 2, 3, 4, 1, 1, 4, 5, 6. B is the matrix 1, 2, 3, 3, 1, 1, 4, 5, 6. C is the matrix 1, 2, 3, 7, 2, 2, 4, 5, 6. Here, A, B, C, they are all square matrices. They are identical everywhere, except the second row. They are identical everywhere, except the second row. And the row vector the second row vector in matrix A plus the second row vector in matrix B equal to the second row vector in matrix C. The second row vector in matrix A plus the second row vector in matrix B equal to the second row vector in matrix C. That means determinant of C equal to determinant of A plus determinant of B. By the theorem, determinant of C equal to determinant of A plus determinant of B. If matrices A, B, C are identical everywhere, except one of the rows, except here, the second row, and the sum of the second row vector in matrix A and B, the sum of the second row vector in matrix A and B, equal to the second row vector in matrix C, then determinant of C equal to determinant of A plus determinant of B. You can verify this determinant by yourself, but an example is not proof. An example is not proof. Let's prove the theorem. Let's prove it. And let's first of all write down the matrices. A is the matrices. A11, A12, A1n. That's the first row. That's the second row. That's the ith row. And that's the nth row. Let's write down the matrices first. A21, A22, A2n. The ith row will be AI1, AI2, AIN. Last row will be AN1, AN2, ANN. That's matrix A. For matrix B, they are identical everywhere except the ith row. So for matrix B, it looks like this. It's also A11 because they're identical everywhere except the ith row. A11, A12, A1n. Second row is A21, A22, A2n. They're identical everywhere except the ith row. Assume the ith row here is BI1, BI2, BIN, and the nth row is BN1, sorry, AN1. They're identical everywhere except the ith row. AN1, AN2, ANN. Matrix A and B, they're identical everywhere except the ith row. And same thing, C is another matrix. They're identical everywhere except the ith row. And the ith row vector in matrix C is the sum of these two row vectors. The ith row vector in matrix C is the sum of these two row vectors in matrices A and B. So the first entry will be AI1 plus BI1. The second entry will be AI2 plus BI2. And the last entry will be AIN plus BIN. That's the ith row in matrix C. We add the row vectors AI1 plus BI1, AI2 plus BI2, and AIN plus BIN. AIN plus BIN. That's the entries in the ith row. The rest are identical. The rest we have A11, A12, A1n, A21, A22, A2n. Last row is AN1, AN2, A, N, N. They're identical everywhere, except the ith row. Next, let's try to show that determinant of matrix C equal to determinant of A plus determinant of B. What's determinant of matrix C? For determinant of matrix C, we can find covalent expansion along any row or any column. Here, let me find a covalent expansion along the ith row. We can find covalent expansion along any row, any column. Here, let me find a covalent expansion along the ith row. Find a covalent expansion along the ith row. The sign for the cofactor, is positive, negative, and so on. Negative, positive, and so on. Positive, negative, and so on. The sign is alternating. The sign of the cofactor is alternating. So, for the first entry here, since we don't know if I is even or odd, we can't tell if the sign is positive or negative. So let me run the sign as -1 to the power of I plus 1. Then take this entry, AI1 plus BI1 times the determinant of the matrix, determinant of the submatrix by crossing out the ith row and the first column. Determinant of the submatrix by crossing out the ith row and the first column, which is determinant of matrix C, by removing the ith row and the first column. Next entry, plus -1 to the power of I plus 2 times AI1 plus BI1, AI2 plus BI2, that's the second entry, times the determinant of the submatrix by crossing out the ith row and the second column, which is matrix C. We cross out the ith row and the second column, plus plus continue. In the last entry here, the sign is -1 to the power of I plus n. I plus 1, I plus 2, eventually it will be I plus n, times the entries AIN plus BIN times the determinant of the submatrix by crossing out the ith row and nth column. From matrix C, we cross out the ith row and nth column. That's determinant of the submatrix C I sub n. That's determinant of C. Next, let's observe. In the first term here, we have AI1 plus BI1 in the parentheses. In the second term, we have AI2, BI2 in the parentheses. And in the last term, we have AIM, BIN in the parentheses. If I distribute, what do I get? If I distribute everything into parentheses, what do I get? If I distribute, let me continue from here. If I distribute everything to the parentheses, I get -1 to the power of I plus 1 times AI1 times determinant of C sub I comma 1 plus -1 to the power I plus 1 times BI1 times determinant of C I comma 1. For the first part here, if I distribute everything to the parentheses, I get two terms. Then for the second term here, if I distribute everything to the parentheses, I get -1 to the power of I plus 1 plus 2 times AI2 times determinant of C sub I comma 2 plus -1 to the power of I plus 2 bi2 times determinant of C sub I comma 2 plus plus for the last term I can also distribute everything to the parentheses. I get -1 to the power of I plus n times A sub I n times determinant of the matrix of the submatrix C sub I comma n plus -1 to the power of I plus n times bin times determinant of the submatrix C sub I comma n. If I distribute, that's what I get here. Now let's observe the determinant C sub I comma 1. That's a submatrix from matrix C by crossing out the ith row and the first column. If I cross out the ith row and the first column, that's a submatrix, which is the same as the submatrix in matrix A and B, because the only difference is the ith row. If I cross out their ith row, then their submatrix must be exactly the same. The only difference in matrix A, B, and C is the ith row. If I cross out the ith row, then their submatrix must be exactly the same. So, determinant of C it can be rewritten as -1 to the power of I plus 1, AI1 stays the same. Determinant submatrix of matrix C by removing the ith row and first column is the same as the submatrix from matrix A by removing the ith row and the first column. Because in matrix A and C, the only difference is the ith row. If I cross on the ith row, they are exactly the same. Plus -1 to the power of I plus 1 times bi1 times determinant of the submatrix bi comma 1. Because in matrix B and C, the only difference is the ith row. If I cross out their ith row, the submatrix will be exactly the same. Same thing here. In the second row, we have -1 to the power of I plus 2 AI2 times determinant of the submatrix submatrix from matrix C by removing the ith row and the second column. That's the same as submatrix from matrix A by removing the ith row and the second column. Because in matrix A and C, the only difference is the ith row. If I cross on the ith row, they will be exactly the same. Plus -1 to the power of I plus 2 times bi2 times determinant of submatrix bi comma 2. That's a submatrix from matrix C by removing the ith row in the second column. Since matrix B and C is the same everywhere except the ith row, if I cross out an ith row, the submatrix will be exactly the same. And continue in the ith row. In the nth row, I get -1 to the power of I plus n times AIN times determinant of the submatrix of A, remove the ith row and the nth column. Because in matrix A and C, they're identical everywhere except the ith row. If I cross on the ith row, their submatrix will be exactly the same. Plus -1 to the power of I plus n times bin times determinant of the submatrix matrix B from matrix B, remove the ith row and the nth column. Since matrix B and C, they are identical everywhere except the ith row. If I remove an ith row from matrix B and C, then their submatrix will be exactly the same. Then, if we observe this value here, the value in the first column here, that's the Covert expansion. That's the Covert expansion of matrix A along the ith row. This is the Covert expansion of matrix A along the ith row. So this is equal to determinant of A. And this is the Covert expansion of matrix B along the ith row. This is the Covert expansion of matrix B along the ith row. So that's determinant of B. Let's complete the proof. Determinant of C equal to determinant of A plus B. If matrices A and B are identical everywhere except the ith row. If matrices A, B, and C are identical everywhere except the ith row, and the ith row vector in matrix A and B, if I add them up, they're equal to the ith row vector in matrix C, then determinant of matrix C equal to determinant of A plus determinant of B. That's the proof for this theorem.